Hi everyone, I am Vignesh Menon, a PhD research scholar in Christian Doppler Laboratory, Athena, in University of Klagenfurt, Austria. Welcome to the presentation of the paper titled Efficient Content Adaptive Feature-Based Short Detection for HTTP Adaptive Streaming, which is also co-authored by Hadi, Amirpour, Mohammad, Ghanbari, and Christian Timmerer. In this presentation, I will introduce the premise of this work and the problem of short detection for HTTP adaptive streaming. Later, I will explain the proposed algorithm and present our comparisons with respect to the benchmark algorithm. Finally, I will present our conclusions and future directions of research. Video streaming over the internet makes HTTP adaptive streaming necessary. It is to cater to a wide variety of devices, network speeds, and user preferences. Each video sequence is split into multiple segments, which are encoded at multiple bit rates, resolutions, and codecs. They are delivered to the client based on the device capability, network speed, and user preferences. For video-on-demand applications in the multi-shot encoding framework, the first step is the shot detection. Each shot is downscaled to set of spatial resolutions and are encoded at a set of bit rates. The low-resolution encoded shots are upscaled to the original resolution and their quality is compared to the original shot. Based on the video quality measures, a convex hull is formed and the optimal resolution is selected for each bitrate for each shot. Therefore, precisely detecting shots will lead to a higher quality of experience or bitrate savings for HTTP adaptive streaming applications. Now, let's discuss the problem of shot detection. In a video, the boundaries between the video shots are termed as short transitions or shortcuts. The process of segmenting videos into shots is termed as shot detection. In HTTP adaptive streaming, the objective of shot detection algorithm is to detect the first frame of each shot and encode it as an ideal frame. The subsequent frames of the shot are encoded with respect to the previous frame via motion compensation and prediction. That is, they are encoded as P or B frames. The short transitions can be present in two ways. Hard shortcuts, where the last frame of the shot is succeeded by the first frame of the next shot. The gradual short transitions like fade-ins, fade-outs. Detecting gradual transitions is difficult owing to the fact that it is very difficult to quantify the change in visual information. Also, since we consider the short detection problem as a classifier problem, that is, to classify the frame as the beginning of a new shot or not, some points to note is that the ratio of ideal frames to non-ideal frames is skewed. The ideal frames are rare in video streams compared to the P and B frames. The cost of incorrect detections is very high. That is, if we miss short transitions or detect wrong frame as an ideal frame, it has negative impact on compression efficiency. Now, we shall look into the proposed algorithm for short detection. The first step of the algorithm is the feature extraction. Here, we compute a DCT-based texture energy function for each CTU of the frame. We compute DCT of the CTU first, and then we apply exponential weighting for the DCT coefficients. We see that higher weightage is given to high-frequency components. The energy values of CTUs are averaged to compute the energy per frame. This figure shows the frame energy values for a test sequence named Tears of Steel. The black circles here denote the frames of a new shot. We observe that there is significant change in the frame energy in those regions. This proves that the feature metric is a good choice for shot detection. We compute the gradient of the frame energy with respect to the previous frame and normalize it with average energy of the current frame. One interesting observation here is that if the gradient value is 0, the current frame is a duplicate of the previous frame. Further, we determine the double gradient of the average frame energy, which is denoted as epsilon. So here, epsilon is the metric we choose to determine the short transitions. The phase 2 of the algorithm is a successive elimination algorithm. As the first step, the entire set of video is scanned. We determine two thresholds T1 and T2 experimentally for classifying the frames as short transition. If the value of epsilon is greater than the upper threshold T1, it is classified as an IDR frame. If the epsilon value is less than the lower threshold T2, then it is classified as P or P frame. No decision is made if the epsilon values are between T1 and T2. Now, the already classified frames are eliminated for step 2. That is, we consider frames with epsilon values between T1 and T2. Q denotes the set of all frames with epsilon values between T1 and T2, and F denotes the video frames per second. In step 2, we consider the distance between the frames for classification. If the frame is more than 1 second after the previous frame in the set, and the next frame in the set is more than 1 second after the current frame is classified as an IDR frame. In step 3, if the frame is more than 1 second after the previous frame, and the next frame in the set is less than 1 second after the current frame, we compare the epsilon values of the frames within 1 second and choose the frame with highest epsilon value as the IDR frame. Now let's discuss the experimental validation of the proposed algorithm. In our experiments, we use JVIT test sequences and professionally produced ultra high definition content which have multiple types of scene transitions. The experiments are conducted in a dual processor Intel Xeon Gold server. As mentioned earlier, T1 and T2 are determined experimentally as 50 and 10 respectively. The benchmark algorithm considered in this paper is the default short detection algorithm in X65. The classifier performance is evaluated using accuracy, precision, recall, and F-measure. In this context, the true event is that the frame is a short boundary, and the positive event is the detection that the frame is a short boundary. The actual shortcuts refers to the ground truth, that is, the number of real short transitions which are determined manually. So this table summarizes the results of our experiments. Though the accuracy measure is comparable, on an average, the recall rate of the proposed algorithm is 25% better than the benchmark algorithm. We also observe that on average, the F measure of the proposed algorithm is 20% higher compared to the benchmark algorithm, which implies that the proposed algorithm is more balanced short detection detector. Using the benchmark algorithm for snow mount and foot market for sequences, the recall rate is 0%. The precision and F measure values are not defined. This is because it failed to detect any short transitions. Using the benchmark algorithm for the fun on the river sequence, the recall and precision values are 0%, and the F measure is not defined. This is because it had only false detections. We observe that our proposed algorithm has worked better in these scenarios. We also estimated the true positive rate and false positive rate to analyze the performance of the short detection algorithms. The better detector is defined by highest true positive rate and lower false positive rate. From the table, it is observed that the proposed algorithm has a TPR of 25% more than that of the benchmark algorithm. It is also evident that the false positive rate of the proposed algorithm is lower than that of the benchmark algorithm. The runtime of the proposed algorithm per frame is evaluated to be 0.1% of the total time taken for encoding each frame. Additionally, the short detection algorithm need to be run for only one representation of the video in HTTP adaptive streaming. The decisions can be reused for the other representations of the same video. To conclude this presentation, this paper proposes a short detection algorithm as a feature-based pre-processing step for X65-based HEVC encoding for video-on-demand HTTP adaptive streaming applications. A DCT-based energy function is identified as a feature to determine short transitions. A successive elimination algorithm is proposed to remove the false detections during gradual short transitions. The final results show that the proposed algorithm has a recall rate of 25% and an F measure of 20% more than the benchmark algorithm, which implies that the proposed algorithm gives a balanced short detections compared to the benchmark algorithm. In the future, this work can be extended to compute the relative complexity of the shots to that of the entire video sequence using the feature metric and predict the ideal bitrate per resolution for each shot. As an extension to this work, more encoding parameters like optimal CU partitioning, quantization offsets can be predicted. This work can be extended to support more recent codecs like VVC. Thank you for attention. I will be very happy to take any questions. Thanks once again.